Alright, Master Mason, no, I know how you snowflakes and marshmallows love this in the mill stuff, so we're gonna go to it. With Schrödinger here, given our equation, so look it up. That's gonna be Hubble's constant, a time in parentheses, dimensional vector, wave function, and a continuance, or there's a few ways to look at this stuff, equal. So this is n1/2 in the parts. That's to say, if the triangulation was this 0, 1 mass gap, 2 mn, actually thermaling that rock up and down, those being the units over distance that determine time, north, how many ups, how many souths. Obviously you're going to have some general relativity involved because, well, you're just gonna. Integrating that in here, again, this is Hubble's constant. This is the determined model of all treads, all pattern, all rock. They're going to burn to the stoichiometric ratio inside of that torch. There you have time, and that's going to be in parentheses because that's our physics now. We're going to start basing numbers off of that field for units and operations, getting things up, getting things down, calling them half operations, and then marking those details as adjusted value or adjusted feeds and speeds to saw A, saw B in programming, HTML, JavaScript. There's different variations that have different adjusted systems for different floor topologies when you understand the timelines and how those vectors lined up to say, that would be that topology somewhere's in here. T in parentheses. That number, I know I need that number. It correlates to a couple of different numbers, x, y, which give me those vectors. I know it can't be up on the paper and towards the opposite wall. I got to move left to right, top to bottom. We use those measurements. That's the constant on paper for Hubble's version of the lowercase version of this being Planck's constant later after the irrational number. The I equals the square root of -1. Somewheres I saw that, Hubble, you're wrong. Schrödinger, Newton, Planck, y'all in my stone mill right now. I'm the radioactive isotope. So that's going to be Planck's constant inside of there. That's that unit 0 to 1. That guy, there's differentials, this guy, there's different times when those things just naturally do things to that element given the topology. And that's going to be coefficient of the derivative. That's what that timeline is. That's that new Hubble's constant, Higgs constant. Hubble's is pretty science and chemistry. Planck is going to go that way with cesium. It's that type of idea. And we're Mn going to say that that constant is the coefficient of that derivative. That number is coefficient, more efficient in co-processes or second orders or something like that. And here on the mill floor, they would still be second orders to the entire mass gap. That's the job. This is training one technique or breaking down that piece out of the model. Deciphering where that would be in its topology there. Zero pullouts, and knowing from the management side, from the safety guy, that's the training model. You'd know the trainer, you'd see that number, and you'd make the triangulation where it is on the floor. T800. And that's coefficient of time, and that's over. We're saying that the coefficient of the derivative is more important than time. Is it times, or is it plus, is it minus, divided by? Given movements from the geometry, X, Y, and Z in its position and location, how many group states and patterns can be made off of that? Well, multiple as long as you're following the rules of the first, second, third order. That's tread, so on and so forth. As we get into here, we can change that value to whatever the radiant is, that time, in parentheses to treads here, or some variable of those numbers in measurement that are already determined in their element. And then I'm looking at X to define Y equals F over X. And so in third order, fourth order operations, we're just taking that triangulation like in the first order and saying the patterns, which patterns normally come off of here, engineer, safety officer, chemist, doing the safety analysis report as an engineer, Hemingway, yeah. Anyways, catch you on the next one.